All right, this is a summary of the things that were illustrated in the last example. The first note is actually going to be a notation thing. So we denote the inverse of f by f with the superscript -1. I actually wrote that on the graph, and then I said I would talk about it in a second. So the superscript -1, it looks like a power. It does not mean exponent. It means inverse because it's on a function. The inverse of a relation changes the x and y values. That's how we ended up finding them, right? Because if a function turns 1 into 4, then the inverse is going to turn that 4 back into a 1. The graphs of a relation and its inverse are symmetric about the line y equals x, and the inverse of a function is not necessarily a function. So the picture every mathematician draws when they have to draw a function. I've got two sets. I've got a domain and I've got a range. My domain has my x's. My function turns x's into y's. My inverse is going to turn the y's back into x's, which means that the domain of f, so domain is where you start. The domain of f is where you end for the inverse function. So it's the inverse is range. And the range for f, so range being where you end, is where the inverse originates, so it's its domain. So that's the relation with those inverse and the functions and the domain and range. That was also illustrated on the previous example. Now, the last point, number 4, was that the inverse of a function is not necessarily a function. So the picture that we had last time, so s was a function, but s inverse was not. And the reason s inverse is not a function is these 2 points right here. Now, these points arise from the fact that in my original function s, there were 2 inputs that gave me the same output, right? I could either plug in 1 or -1 to get 4, either one of them. So then when I do my inverse, so my inverse is saying, what should I plug in to get 4 out? Well, the answer is either positive or -1, okay? So with functions, we had the vertical line test. With inverses, we're going to have a horizontal line test. So what we need to ensure that the output is a function is what's called one-to-one. The fact that there were 2 different inputs for one output was a problem. So we want to make sure that that doesn't happen to guarantee that our inverse is a function. So to guarantee So we're going to need it to be what we call 1-to-1, meaning 1 input, 1 output. There's 1 input for every output. Now, a function, remember, was there's 1 output for each input, meaning if you plug in a number, only 1 number came out. So if I plug in 1, only 4 ever comes out. I don't also sometimes get, -20. So that was a function. 1-to-1 is going to say not only does 1 thing in, 1 thing out, but there has to be only 1 way to get a specific output. Okay, so it's not enough to just be a function. I need to make sure that if I need the number 4, there's only one way to get the number 4. And that's the difference between our one-to-one. And that also is going to give us, so graphically, that's going to give us the horizontal line test. So horizontal line test. A graph represents a one-to-one function provided, just realized I did not even close to have that on the camera, sorry. So a graph represents a one-to-one function provided provided that no horizontal line intersects the graph more than once. Again, I'm going to bring our picture from the first example. So a graph represents a one-to-one function provided that no horizontal line intersects the graph more than once. Right here, these guys lie on a horizontal line, so that when I reflect and turn it into the inverse, they lie on a vertical line and it's not a function anymore. All right, so let's look at a few examples of, are they one-to-one? So I just graphed these in Desmos real quick. So does this function represent something one-to-one? Well, there's a whole bunch of horizontal lines here, and I'm seeing that they intersect more than once, right? Because this line at 4, I can either plug in 2 or -2 in, and I get out 4. Same with 1. I can either plug in 1 or -1. So this is x squared. It is not one-to-one because there's different ways to get the same output. Now, if you were to graph, so suppose I graphed okay. So look at this, right? Here's my x squared. Here's my reflection. It's a parabola that's on its side. This parabola that's fallen over is not a function. So the original was not one-to-one. It didn't pass the horizontal line test. So the resulting inverse is not one-to-one. Now you'll notice the way I typed this in Desmos, I had to type 2 different things, right? I did square root of x and negative square root of x. If we take this thing away, this is, oops, there. So this blue is our root x function. Now, if I restrict, I can restrict like domains of stuff to make them one-to-one. So if I throw away this branch of my x squared, then it is one-to-one. It would pass a vertical or horizontal line test, so that its inverse would be a function, which is why our square root of x looks like this. Okay, so that's just an aside about x squared. Let's look at this, 3x minus 5. So it's a line. It's going to pass our horizontal line test. Linear functions always pass a horizontal line test. If I want the number 15, there's only one number that when I multiply by 3 and subtract 5 is going to give me 15. So this one would be one-to-one. And then the last one I have is 2x cubed minus 1. This is one-to-one. So I can imagine zooming out a whole bunch. This is one-to-one as well. The only place that maybe one might be concerned is here around 0. But if you were to zoom in close enough, you'd see that it's not actually horizontal. It's just close to it. Okay. So anything that ignores negatives, that's a really classic not one-to-one example. Anything that has a bowl or a V or a U shape is not going to be one-to-one. So that's our horizontal line test. Now the other thing that we would be interested in doing is finding equations for functions and relations given the original function. So in the next video, I will actually go over how to do that.